Alright, so for today's session, I'm going to talk about a problem that I proposed. This is probably the first problem that the first math Olympiad problem that I ever proposed in my life. And it was selected as this year's Malaysian IMO team selection test as problem 5, which I was pretty proud of and being really honored. So yeah, let's go to the problem statement. So what it asks is that it asks to find all the functions from integers to integers such that this number AB plus BC plus CA and also FA FB plus FB FC plus FC FA have the same set of prime divisors for all the integers A, B, and C. So yep. Now before I jump into the solution of the problem, let me just talk about some story about this problem and how I got to propose it. So yeah, you guys are probably curious how I thought of this problem. Well, in fact, it was created 10 years ago, right after IMO 2012, and it was indeed inspired by this problem from IMO 2012. So same thing, you are asked to find all the functions from integers to integers, but but those functions need to satisfy uh, this functional equation instead. So just in case you are wondering how you are going to solve this problem from the IMO, well, let's do some basic A equals B equals 0, you get F0 equals 0. And also if you plug this one, you get FA equals to F negative A, which means that this function is this function is basically even. Now the third one is pretty much a bit of clever maneuver, and if you plug this one, you basically get into some quadratic equation and you end up with this form, which in hindsight is pretty useful. Now, once you get into this form, what you need to do is to study this tree as in like, okay, you get F1 and then you want to see like how F2 would behave. And if you do this sufficiently long enough, you will end up with 3 leaves over here. Each leaf corresponds to one function class. So yeah, this looks simple, right? No, it's not. Now to talk a bit about like how how I feel about this problem. Well, I was part of the IMO 2012. In fact, I was a contestant for Malaysia, and that was my second IMO for the IMO 2012 in Argentina. And that morning before the contest, I actually felt pretty energized because I got 2 problems from day one. And that put me into a reasonable position to aim for a gold medal for that year, which also means that I have to get problems 4 and problems 5. So when I checked the paper at the first glance of the paper, this was the first problem on the list, which means that it's supposed to be easy. So hey, I decided that why not I give it a try first. And then I got the first two, f0 equals 0, and also the evenness of the function f pretty quickly, I would say. And probably also the fact that if fc equals to 0 for some c, then f has a period of c. But for some reason, I did not jump into this quadratic equation. And instead, I tried to kind of like study this tree first, meaning that I will fix f1 and then see like how f2 should behave. And sure, I got 2 cases for f1 and 0. And indeed, the case where f2 equals to 0, I immediately get that this f must have a period of 2. But this one, f2 equals to 4f1, this is the one that is tricky because when you study f3, there are 2 more cases. And from here, you can branch out to the 2 more cases for f4 and then 2 more cases. So you basically get into like in my mind that time that there was like what exponentially many cases. And things just got downhill from that point because I started to panic because there were just like too many cases to consider based on this observation itself, and I was naturally not sure what to do. And by the time I could figure out that hey, like some of the leaves just do not exist, it was already a lot of time passed. And by the time I finished writing the solution, there was only 1 hour left. And if things it was not worse enough, that then if things was not bad enough, my solution right up I thought was pretty messy. Partly also because like this also because like the checking of this function, i.e. like checking these three classes of function work, is far from trivial, and there are just a lot of cases to do. So in fact, my solution that time there were four full pages of writing, and also five more pages of scratch writings. So I ended up spending another 45 minutes to check the solution to make sure that I could reasonably get a 7 on the problem. And that left me with 15 minutes to try problem 5, which also means it did not happen, unfortunately. Now, my three other teammates had a different problem. They got problem 5 pretty perfectly, but all three of them lost marks on problem 4 from some reasons. So in fact, two of them uh, missed out the case of period 4, which is case C, and they got penalized very heavily for that. And the other one, he got everything here, but he did not do a full verification of the tree function class, which, as I said, was involved a bit of casework, and that cost him like I think 2 marks, if not mistaken. So yeah, overall, I would say that that day two was not exactly a good experience for any of us, and therefore you can also think of this problem as my problem proposal as a revenge against this problem, I guess. Well, I mean, this to be fair, this problem was pretty nice. It's just that the solution process was not that was not that straightforward or elegant, I would say. Well, I mean, of course, if you think that revenge was too dark, I mean, we still had a pretty good experience on IMO 2012. I mean, it was winter. We stayed in the hotel most of the time, but we still enjoy the scenery over there. So yeah, as a tourist, that was an excellent experience. Just for the IMO contest itself, eh, well, all right. So now I'm going to talk about how you are gonna solve the problem that I proposed for the Malaysian IMO TST. So recall that this problem is like that. Like for each prime P divides the left hand side if and only if P divides the right hand side, which means that both these numbers have the same set of prime divisors. The first step you do is probably something very routine, very basic. So you just try to substitute some very basic values and see what happens. And this is indeed the key to advance to the next steps of the solution. So in particular, what you would do is to substitute things like, for example, A equals B equals C equals 0, because this would force the left-hand side to be 0, and therefore the right-hand side also has to be 0, and therefore F0 equals to 0. Now, what happens if you do ABC equals to 1 plus minus 1 and 0? Well, the left-hand side is plus minus 1, and the right-hand side also has to be plus minus 1 for this reason, because of the same prime divisors condition. It would turn out that the right-hand side will be things like what? F of plus minus 1 and times F1, and therefore you would know that F of plus minus 1 has to be plus minus 1. And finally, if you substitute A equals to 1, B equals to anything, C equals to 0, then the left-hand side is just B, and the right-hand side is F1, FB. And therefore, we see that B and FB must have the same set of prime divisors as well. Now, what's next? Usually for functions like this, the typical steps will be try to guess what are the properties of the functions and try to prove them. But what exactly are the properties that we are looking for? So all these things, I would say, typically comes with some experience. But in this case, we see that things that are typical to try are things like injectivity, surjectivity, whether it's odd or even, whether it's linear, etc., or whether things it's multiplicative. And it turns out that for all the things that I say just now, not all of them are true, but most of them turn out to be true. For example, things like injectivity, it's true, and surjectivity, it's odd function, and it's linear. Now, the issue is that even though we could guess them, it will still take some effort to prove them, and proving some of them is easier than others. So it turned out in this case, injectivity is the easiest to prove. Based on this intuition over here, I'm not sure how to explain why is it so. Whereas for showing that it's linear, it's probably a bit too much to ask unless you have some other foundations built. In any case, I should stress that for the rest of the solution, a lot of times we'll actually set the left-hand side to be 0. And this is because it will force the right-hand side equals to 0 as well, and this makes it easier for us to establish something. Well, technically, we could also do left-hand side equals to plus minus 1, but this is a bit trickier, I would say. For the first step, we are going to start small and show that f is injective. How are we going to show that it's injective? Well, the same classical trick applies. Suppose that you have two numbers a1 and a2 that have the same values, f of a1 equals to f of a2. Now, naturally, you like what I said before, you want to substitute such that a is either a1 or a2, and then ab plus bc plus ca equals to 0 because it will force the right hand side to be 0 as well. And what's nicer is if b is the same as c, and fortunately, these three things would work. So a1 minus 2a1 minus 2a1. If you substitute this to the right hand side, you get expression like this: 2 fa1 f of minus 2a1 plus the square of the f of minus 2a1. But since we have already assumed that f of a2 is the same as f of a1, this expression turned out to be the same as this expression, which is equal to 0. So what we also have is 2 f of a2 times f of negative 2a1 plus the square of f of negative 2a1 is 0. In fact, this is the same as changing a to a2 and keeping b and c to be same as minus 2a1. And therefore, we would also get that this ab plus bc plus ca in this form, except a equals to a2, must be 0. So what we have is this equation of degree 2, which also means either a1 equals to 0 or a1 equals to a2. If a1 equals to a2, then we are done because this is exactly what we want for injectivity. But what happens if a1 equals to 0? Recall that for each integer b and fb must have the same prime divisor. So, f of b and fb must have the same set of prime divisors. So that means that f of 0 has to be 0, and f of not 0 is not 0 because any non-zero number only has a finite set of prime divisors. So yeah, this is how we show injectivity. The first checkbox is done. Now let's move on to show that f is odd, meaning that fa plus f minus a is 0. You might ask, why do we want to show this? Well, before we even start to do all those technical stuff, we probably want to guess what the solution would look like. So in particular, we know that the identity function would work, and we probably guess that all the functions have to be some sort of identity function-ish. That is true, but we probably need something to show this. So having shown that the function is odd will probably help us. But in order to show this, we need something technical, i.e. we need some groundwork being done. So here comes the lemma that we are going to show. If x and y are not 0 and a is a finite set of prime numbers, then there is an integer c and a prime number p not in a such that p divides x plus y f c. Why would this lemma be useful? Now the intuition would be that if y is the same as fa plus f minus a and this is not 0, then we can find a prime number p that is not in our favorite set such that p is P divides X plus Y FC, and therefore this would violate the fact that the left and the right hand side of our original equation must have the same set of prime divisors. And to, to illustrate how we would show this fact, right? Now, what we would do is to single out one of the factors, say x prime plus y prime FC, and show that x prime plus y prime FC cannot be divided by any of the prime numbers in A. And if x prime plus y prime FC is not plus minus 1, then it has to be divisible by some prime number, right? So this prime number must come from outside of A. So that's the whole idea. Now, to put this into words, let's go with the same the same classical trick saying that, okay, if x and y have GCD equals to u, x equals to x prime u, and y equals to y prime u, then x prime and y prime are relatively prime to each other, meaning that they have GCD equals to 1. Also, let x to be the set of prime numbers dividing x prime y prime. Now, instead of choosing C directly, we choose the prime numbers of we choose the prime divisors of C. So in particular, for each P in A union X, we choose P such that P divides C if and only if P is not in X. Notice that I did not say anything about the prime that is outside A union X, which means that those primes are kind of free. We can basically do whatever we want. Yeah, we will use this fact later. So since C and FC must have the same set of prime divisors, this fact would also hold for FC. And the fact that the GCD of x prime and y prime is 1, meaning that they cannot share the same prime divisor, shows that for each of the prime P in A, P divides exactly one of these three numbers, x prime, y prime, and FC. So in particular, this would also mean that P would divide exactly one of these two numbers, either x prime and FC times y prime, but not both. This would force the fact that P cannot divide x prime plus FC times y prime for each of the prime in A. Now, going back to the choices of C, we say that we already specify the prime divisors of C if the prime divisors come from A union X. But we did not say anything about the primes that are outside A union X. So first of all, let's show that why this thing is valid, meaning that we can choose such C. Well, that's because we assume that A is finite and X is finite because X prime, this small x prime and small y prime, these are both non-zero numbers, and therefore they must have finite number of prime divisors. So that means that we can choose. That means that A union X is also finite, meaning that we can just take, for example, like C equals to the product of all primes that is in this A minus X, and potentially multiply by any finite set of prime numbers that is outside of A union X. So long story short, this also means that there are infinitely many primes that are outside A union X, which also means we have infinitely many choices of C. So all we need to do is to choose x prime plus FC times y prime. All we need to do is to choose C such that x prime plus FC times y prime is not plus minus 1. And why can we do that? Well, all we need is 3 choices of C, which we have infinitely many of them. So 3 choices is just pretty simple. And we already have the fact that F is injective, meaning that there are 3 different choices of C, for example, which will correspond to 3 different values of FC. So one of them must be such that x prime plus FC times y prime is not plus minus 1. And since this is not plus minus 1 and cannot be divisible by any prime in A, it has to be divisible by some prime, so this prime must come outside of A. So if this prime is Q, then we have Q divide x prime plus y FC times y prime. And this thing is divisible by U times the whole thing, which turned out to be the same as x plus xc fc times y. To go back to the original proof on why f has to be odd, so suppose that for some a not equal to 0, we have fa plus f minus a not equal to 0. Well, why can we assume that a is not 0? Because if a is 0, then both of these have to be 0. So let's pick b equals to minus a. Then ab plus bc plus ca is minus a squared regardless of c. And for the right-hand side, we basically have this form. Set x equals to fa times f minus a, y equals to fa plus f minus a. Then the right-hand side is just x plus yfc, which is exactly what we want from the lemma. Now, we assume that y is not 0, and x cannot be 0 because both a and minus a are not 0. So by our lemma, if we set the capital A to be the set of primes dividing A, then we can choose C such that for some prime Q that is not in capital A, i.e. Q does not divide A, Q divides x plus yfc. This would directly contradict the fact that negative A squared and x plus yfc must have the same set of prime divisors. So this is a pretty short conclusion of the proof where f is odd, only because we have already established the sublemma. Now let's show that f is linear, i.e. fc equals to cf1. This is also the last step of our solution, which also means that this is not supposed to be easy. So let's start with a failed attempt that I came out when I tried to solve this recently because I realized that this did not work. And then I checked back my solution that I wrote up 10 years ago after I proposed the problem and realized that, okay, there needs to be something done. But why do I show this? Because this is more intuitive. So as per most of the arguments, we will try to use induction. Well, we can also only consider C that is greater or equal to 1 because we have already shown that f is odd. So the base case C equals to 1 is trivial. And then we have this inductive step, and then we try to choose triples minus C, C plus 1, and C times C plus 1, such that the left-hand side is 0. Now notice the problem over here where we have to deal with f of c times c plus 1, which we do not know how to do because all we have is all the way f of 1 all the way up to c. So how do we do that? Well, there is one trick in Olympiad saying that if showing something that is very specific does not work, try to show something that is more general because that might give you some more powerful building block. And this is exactly the case over here. So let's instead show that for all C and A, f of CA is the same as C times f of A. So as usual, we show that we consider induction and then consider only where C is positive. And also A is not A non-zero because if it's 0, then both sides are just 0. Now, how do we plug the triples? So instead of doing minus C, C plus 1, and C, C plus 1, we multiply A by each side. And of course, we call that A is not 0. So the left-hand side is still 0. The right-hand side can be split in a nicer way right now because just now we were worried about like what, or we did the fact that we did not deal with f of c times c plus 1. But now over here, AC C plus 1, we can actually bring the C out simply because we have a stronger building block. And as for f of minus CA, it's just we can still bring the C out. And as for AC plus 1, we leave it as it is. Now the right-hand side has a nicer form and actually factorized pretty nicely. Well, I should also mention that f of minus CA equals to minus C times FA is the result of showing that f is odd, and therefore you can also bring the negative out. Since C is non-zero, and because it's greater than 1, greater or equal to 1, A is non-zero, and C plus 1 cannot be 0 either, so this thing cannot be 0, which means that the last factor has to be 0. But this is exactly the same as saying that f of A C plus 1 is the same as C plus 1 times FA. And therefore we are done. Now, we have already shown that F is linear, i.e. Fc equals to C F1. But F1 can only be plus minus 1, so we are left with only two solutions. Fx is x or Fx is minus x. So either the identity or the negative of the identity. As for all the functional equations, we have to verify that the functions that we suggested would work. But in this case, it's pretty straightforward because the left-hand side is the same as the right-hand side, which is AB plus BC plus CA. So this is also something that is a bit different from the IMO 2012 problem 4, where the letter has a really tedious, relatively tedious verification process because there are a lot of casework. So, yep, that is all the presentation I have. Thank you very much for listening.